So welcome everybody to the Atto Fridays. This is going to be the last one of this season. Then we're going to take some time off, also to take care of our lives. We're very happy to announce today's speaker, who is Professor Ignacio Franco. He is an associate professor at the University of Rochester, and research in the Franco group focuses on theory and computation as it applies to dynamical processes occurring in molecules, nanoscale, and extended systems. So in fact, much bigger and much longer than the Atto Fridays typical topics. But the group is particularly interested in exploring quantum frontiers in molecular science and in developing new methods to probe and control the behavior of matter by means of external stimuli, a topic that they like to refer to molecules under stress. So we are all very stressed here because we have been doing this also for a while. Ignacio received his BSc in chemistry from the University of Columbia in 2001. And in 2002, after completing his diploma program in condensed matter physics at the Abdus Salam International Center for Theoretical Physics in Trieste, he moved to the University of Toronto to pursue a PhD in theoretical chemical physics under the guidance of Paul Bloomer. So today the talk is Fridays, physics, chemistry, and so on. And in 2008, he joined Northwestern as a postdoctoral fellow in the groups of Mark L. Ratner and George Schatz. And in 2011, he moved to Berlin to take a position as a group leader and Humboldt Research Fellow in the theory department of the Fritz Haber Institute. And in 2013, he joined the chemistry faculty as an assistant professor and was promoted to associate professor in 2019 and to full professor in 2024. Ignacio is the recipient of the NSF Career Award, the OpenEye Outstanding Junior Faculty Award of the American Chemical Society, the Leonard Mundell Faculty Fellowship, the Curtis Provost Teaching Award for non-tenured faculty, and the College Award for undergraduate teaching and mentoring. So lots of awards. We're happy to have him here. He's a South American, has also been in Berlin. I think we share this. And today he's going to talk about light field control of real and virtual charge carriers. So we are happy to start. Ignacio, the floor is yours. Feel free to take it. We're ready to go.
So, Carla, thank you so much for this wonderful invitation to be part of these quantum battles. It's my first time that I'm part of a quantum battle on a Friday. And I look forward to just communicating with this community, telling about this community some of the work that we're doing. And in particular, what I would like to focus on is on how to control electron dynamics using the subcycle structure of light. I mean, let me start just by telling you where I'm calling from, where I'm presenting from. So here's the city of Rochester. This is the University of Rochester right here. This is the River Genesee. And then at the end of that, you see Lake Ontario. So this is upstate New York. Because Rochester is the land of the Kodak company, we are also technically the land of the Kodak moment. So that's the fun fact of the day. Well, let me start by saying something that I think we can all agree with. Molecules are pretty amazing quantum systems. They have manifolds of transitions in many regions of the electromagnetic spectrum. The electronic degrees of freedom give us transitions in the UV-vis, the vibrations in the infrared, the rotations in the microwave, and so on. These energy levels can be chemically tuned. You can assemble into complex architectures. And so they're pretty amazing and highly compact quantum systems. And for this reason, ever since the inception of quantum mechanics, a long-standing direction in chemistry has been how to use quantum coherence and other non-trivial quantum mechanical effects to enhance molecular function. And this is a direction that my group at the University of Rochester responds to. And in particular, we work in four different topics. We work on the quantum control of matter at the level of electrons. This is the subject of today's lecture. We also want to understand, because we're interested in quantum control, we have to think very carefully about quantum decoherence. And so we work very carefully on how to understand quantum coherence in matter, how to protect it, and so on and so forth. Another topic that is very close to us is the problem of quantum transport across molecular junctions. And because we all need to compute this, we worry about the problem of quantum simulation, both in classical computers and in analog and digital quantum computers. Okay, so the topic of today will be how do we control matter at the level of electrons using coherent laser sources. And the reason why we focus on electrons is because they determine the optical properties, the transport properties, and effectively the chemical reactivity of matter. And the reason why we focus on lasers for the control instead of conventional means, and by that I mean an applied voltage or thermodynamic or chemical control, is because if you're able to do it with lasers, you can do it on ultra-fast timescales, on ultra-femtosecond to attosecond timescales. And in particular, a direction that is of great interest to me and to several people in I think in the ultra-fast community is the idea of trying to develop electronics that instead of operating at gigahertz frequencies like the conventional electronics, we are now trying to push electronics toward the petahertz limit, so about 1,000,000 times faster than conventional electronics. And for this, we need ultra-fast laser sources, such as those provided, ultra-fast sources such as those provided by light. Okay, so a general topic in my group has been how to control electrons in matter using coherent laser sources. And we have advanced 3 different directions over the years. We have advanced the concept of how to induce currents along nanojunctions using lasers. This will be the main subject of today's talk. Another general concept is how to use non-resonant light that through Stark effects, it leads to control of electron dynamics at cross interfaces. This is the phenomenon that we call the Stark control of electrons across interfaces, or Shelley. I will hope to tell you some of the basic concepts in here too. And a third topic that we are very actively working on right now is the concept of Bloch engineering, and in particular, how to use non-resonant light to dress materials with light and then impart properties, emerging properties that are very different from those observed near thermal equilibrium. Okay, so let me tell you about the phenomenon of laser-induced spatial symmetry breaking. So the system that we have in mind is a junction. So this is a metal, this is some material, and this is another metal. So it's a typically a nanoscale to microscale junction. The material in here, it could be a molecule, it could be a semi-metal, it could be a semiconductor, or it could be a dielectric. So it's any type of material in here will work. The regime in which we'll be working on is one in which the whole thing, metal, molecule, metal, or metal, material, metal junction is spatially symmetric. There will be no bias voltages. And what we're going to do is that we're going to come in with a very special class of laser fields, and we're going to break that spatial symmetry and generate a current. And because these laser fields, I mean, the envelope of these laser fields, you can manipulate on, you can turn them on and off on femtosecond timescales. What this will do is that it will generate bursts of currents on femtosecond timescale, which is essentially a new current standard. What do you need for this? So the basic physical ingredients here is you need a laser field that has a relatively low temporal symmetry, and I will tell you what this means. And you need the nonlinear response of matter to such laser field. There is no quantum control in linear response. And the traditional example is an electric field of light that has a frequency component of omega and another frequency component at twice that frequency of 2 omega. And if you now look at the response of matter to such laser field, and in particular for symmetry breaking, you're interested in whether that laser field can generate a dipole or a current that survives time averaging, and these lines here means time averaging. Now, in linear response, if you calculate the time average of the current, that will go to the linear power of the electric field, and because these sources are AC sources, the time average of this electric field will be 0, and on average, you will generate no net dipole. The second order will be 0 because you're dealing with a system that is centrosymmetric, no? So that the second order response is 0. And then the first non-trivial order in the response will be one that depends on the cube of the field. And once you have that cube response, so through the nonlinear response of matter, what the material is doing is that it mixes the frequencies and harmonics of the laser field, and it generates a zero frequency component in the response. So for example, you could, through nonlinear response, you could have omega plus omega from this component of the laser field minus 2 omega from this other component in the laser field, and that will lead to a zero frequency component in the photoinduced dipole of currents that generates this laser-induced symmetry break. And you see those laser-induced currents or net dipoles, you can manipulate the sign and magnitude simply by varying the relative phase between the omega component and the 2 omega component of the laser field. Okay, and this is the phenomenon of laser-induced symmetry breaking. Now, experiments nowadays don't use these very long coherent laser sources, but how experiments look like right now is that they use electric fields that are very, very short. And in fact, those laser pulses are so short, about 10 femtoseconds or 4 to 5 femtoseconds, that they admit only a few optical cycles during the laser field. And to a rough approximation, you can think of this electric field as some envelope function, maybe a Gaussian function if you're lucky, times a cosine. This is the central frequency of the laser pulse. And then you have a phase, and this phase is called the Kerr envelope phase. And these few cycle laser pulses, the reason why they're so very interesting is because they are so short that you can apply very strong laser fields before inducing dielectric breakdown. So in fact, you can apply electric fields with amplitudes between 0.1 to 2 volts per Armstrong, or intensities of 10 to the 11 to 10 to the 13 watts over square centimeter, before you actually rip electrons apart or you induce dielectric breakdown. So you can access a non-perturbative regime of the light-matter interaction, something that you cannot capture through finite order perturbation theory, without ionizing the material or inducing dielectric breakdown. Now, these type of laser fields lead to control of electron dynamics on the femto to attosecond timescale. The femto part is easy to see because the whole laser field is just few femtoseconds long. The atto is very interesting. So the reason for this is because at these laser field amplitudes, the material, instead of responding to the envelope of the laser field, like in Rabi type of physics, what you find is that the material responds to the instantaneous value of the electric field. So it really sees the instantaneous value of the electric field. And maybe your control is not because of the whole laser field, but maybe your control is just because of this component of the laser field, which is stronger than any other component that you have generated. So even when the laser field could be a few femtoseconds in length, in time, the control may be because of this subcycle structure of light, and that control now becomes attosecond, in attosecond timescales. Yet another reason why these laser fields are so very interesting is because they can be so strong, they can lead to very non-trivial Stark effects. In fact, the Stark effects that you can generate with those laser fields are so strong that you can turn an insulating material like fused silica, like glass, now with a 9 electron volt energy gap, into a transient metal, into a metal for a very short period of time. So it's definitely not a small effect. Now, the main source of control in these experiments is what is called the Kerr envelope phase. And the Kerr envelope phase, I'm just going to show you what it does. By changing the Kerr envelope phase, what you're doing is you're changing the temporal profile of that laser field. And for some Kerr envelope phases, the field may be, for example, symmetric with respect to time inversion, something like this. So this is a field that is symmetric with respect to time inversion right at the center. Or you could have another type of laser fields, for example, with a phase of pi halves, which are now antisymmetric with respect to time inversion. So just by changing the Kerr envelope phase, you're varying the degree of time asymmetry of your laser field. And that will have a very strong implications in the control. Okay, so I'm going to claim that the first proposal to use the subcycle structure of light to generate currents was done by me as a PhD student at the University of Toronto, working with Paul Brummer, in which we were thinking about a long molecular system, polyacetylene connected to metallic contacts, and through Stark effects, we were using the subcycle structure of light to generate currents. And the first experimental demonstration of this concept was done by the group of Ferenc Krauss, and in particular by Agustin Schriffen, in this paper, a paper that changed my life, in which what they did is that they had a few silica connected to macroscopic mold contacts, and they have so essentially they had a junction that was just 50 nanometers in width, and they had a polarization of the laser field across this junction direction. And by using this few cycle laser structure, they were able to generate net currents along this spatially symmetric system that could be controlled simply by varying the current envelope phase. And the type of results that they were able to get, this is the amount of charge that they were able to extract as a function of the current envelope phase. And the experimental results are shown in green. And you see that just by varying the current envelope phase, you could actually choose whether the electronic current that you're producing moves to the left or to the right, or for some phases, for example, of a phase close to pi-halves, you will get a current that is approximately 0. And we spent, once this experiment appeared, we spent many years trying to understand every nook and crack of that experiment, and our understanding of this experiment is summarized in this paper that is already a few years old. Okay. Now, ever since, there has been impressive experimental progress. This slide is already a little bit outdated. There are many exciting experiments occurring in 2023 and 24, but it gives you the main concepts. So there is a second generation class of experiments by the group of Peter Hummelhoff, in which what they do is that instead of having few silica, they have graphene connected to metallic contacts. They're applying lasers with few cycles, and they generate currents. And they manipulate the currents by varying the current envelope phase of this laser. There are experiments, I think, initially done by Rupert Hoover and now in different parts of the world, including the US, in which now what they do is that you have an STM tip and a surface, and you have a molecule, and you have a laser field that is maybe in the infrared or maybe in the terahertz. And what this is doing is that it generates an ultrafast voltage across this junction. And what this allows you to do is to do scanning tunneling microscope imaging, but with ultrafast control. So now you can watch chemical reactions on surfaces and things like this. There is another class of experiments mostly by Alfred Leighton-Stoffer, in which what he's trying to do is a strong field control with weak field excitations. So he's using metallic nanostructures to work as an antenna that that leads to like also strong field control even when you have weak field excitation. There is another class of experiments in which you can measure electronic coherences directly by measuring currents in a sort of like a bump-probe excitation, in which a first pulse creates a coherent superposition, and the second pulse generates the ultrafast current, and you can look at the ultrafast current as a measure of your ability to preserve coherences in this system. So it's an interesting time for this class of this direction of research. Okay. And what I'm going to show is work that we did with the group of Peter Hummelhoff, and in particular Tobias Weitz, who changed his surname from Bulaki, and Christian Heide, and from Antonio Garzón, who was working in my group. And this is a wonderful collaboration. I love this collaboration because we all contributed in non-trivial ways, and we were able together as a team to get to a place that none of us could have gone individually. So this was a great honor in my life to be part of this team. Okay, so here's the hypothesis. we're thinking about experiments that Peter is doing, in which he connects graphene to metallic contacts. And the hypothesis is that there are two types of carriers in the generation of currents. One that we call real charge carriers, and another one that we call virtual charge carriers. And I will explain what I mean by this. And the further hypothesis is that just by changing the carrier envelope phase of the laser field, you will be able to trigger either one of the charge carriers. For example, for a carrier envelope phase of pi halves, the hypothesis is that we would generate the real charge carriers. But for a carrier envelope phase of 0, the hypothesis is that we will generate virtual charge carriers. I'll explain. Okay, so let me explain what I mean by the real charge carriers. So by the real charge carriers, this is the regular type of photoexcitation. You come in with your laser field, you create electron hole pairs. These electron hole pairs survive after your laser pulse is done. And because your laser field has a relatively low temporal symmetry, because you have this Fushaku structure, you will give these electrons and holes a kick in momentum space. They will travel through the material and they will be collected by the gold electrodes, forming a net current. And the hypothesis is that this happens for a carrier phase of pi halves. The other type of charge carriers is what we call the virtual charge carriers. And we call them virtual because they only exist during photoillumination. Now, after photoillumination, these virtual charge carriers will cease to exist, and this it's completely analogous to what we call transient excitations in a material or virtual states. No? So, what's the idea? You have a laser field, and this is the hypothesis is that these carriers occur for a laser field with a carrier envelope phase of 0. And this is the time structure of that laser field, and you see is more intense for positive amplitudes than negative field amplitudes. So the hypothesis is that this laser field, what it will do is that it will generate a transient dipole in the system. So it will shake the electronic cloud. And because we're thinking about a nonlinear optical effect, and this field is more intense for positive amplitudes than for negative field amplitudes. So that means that the dipoles that we generate in this problem, the electronic cloud will be pushed more in one direction than the other one. You will have a net dipole during photoexcitation. And if the material was not connected at all to any metallic electrodes, after the laser field is done, any excitation that you generate in this process will decay because it's a non-resonant effect, and then the net absorption of energy is suppressed. But now, if you generate this transient dipole during the laser field, transient net dipole during the laser field, and now you're connected to metallic electrodes, what happens is that those metallic electrodes will take this transient dipole and turn it into a current. And this is what this picture is supposed to represent, in which you generate this transient dipole, but because you're connected to these gold electrodes, this transient dipole turns into a current. Okay, so the main thing is that this photoexcitation only happens during photoillumination. Okay. Now, there's some suggestive evidence for this hypothesis. There was a temporal symmetry analysis that we did many years ago with Paul as a PhD student, in which what we were showing is that for continuous wave excitations and closed systems, if you had a field that was symmetric with respect to time inversion, then you could guarantee that there were no momentum that will survive, net momentum that will survive time averages. And for this, for me, this meant that no real charge carriers were possible. And what we also showed is that if your field was antisymmetric with respect to time immersion, then what you could show is that for this class of excitation, you will not be able to generate net dipoles that survive time averaging. And for me, this meant that no virtual charge carriers are possible. So even when this was suggestive and inspiring, the caveat with this is that this whole analysis is valid for continuous wave excitation plus closed systems, while the experiments are done with few cycle laser pulses and manifestly open systems. So we were not sure whether, it was not clear whether this type of symmetry analysis will apply to that class of problems. The other piece of evidence that we had were two main experiments, or the two main experiments at the time in which we're starting to think about this. So there were the experiments that I discussed by Ferenc Krauss, in which he had gold connected to, a silica nanojunction, in which you had silica sandwiched between two gold electrodes. The whole junction was 50 nanometers. And what they record here is the amount of charge that you can extract as a function of the carrier envelope phase. And what you see is that the maximum charge that you can extract is right there at the carrier envelope phase of 0. And there was another class of experiments, the ones by Peter Hommelhoff and his group, in which they had graphene connected to gold. And the main difference, I will say, in addition to the material with respect to this, is that instead of being a 50 nanometer nanojunction, this was a 5 micrometer nanojunction, so much larger. And the way that Peter and his group like to plot their data is that they do these polar plots in which they increase the amplitude of the electric field from radially from 0 to 1 to 2 to 3 volts per nanometer. And they record whether the current is positive in red or whether the current is negative in blue. And the Kerr envelope phase of the laser field goes radially. And what you see is that the maximum charge, the maximum effect, the maximum current that you can generate is for a Kerr envelope phase of pi halves, or in the other direction, 3 pi halves, while for a Kerr envelope phase of 0 or pi, not much is happening. So you see very related experiments, closely related, both in junctions, and what they see is that they see completely different Kerr envelope phases where they get the maximum control. The smaller junction gets a maximum for a Kerr envelope phase of 0, while the large junctions gets a maximum for a Kerr envelope phase of pi halves. Okay, so to be able to model this type of processes and test this hypothesis, you need a method that not only allows you to capture the quantum dynamics of electrons in matter in bulk, but you need a method that is also able to capture interfacial effects. And there are many calculations out there in the literature in which they model these processes in nanojunctions by considering the material as if it was in bulk. And as I'm going to show you, what those calculations, they get the bulk properties correctly, but what they miss is the interfacial effects. And these interfacial effects can be very important or even dominant in a dominant component of the mechanism at play in these laser-induced currents. Okay, so the main method that we use to do this is what is called the time-dependent non-equilibrium Green's function method. So essentially what we're doing is that we're solving the Liouville-Voigt-Neumann dynamics for electrons in matter in the presence of a laser field. And we assume that the dynamics in the system is unitary, and we capture the effects of the gold contacts through these additional terms in the equations of motion that just make sure that to absorb electrons that arrive at this interface and to eject them back in to such that at the end of the day, the system goes back to thermal equilibrium. So these are charge injection and absorption terms. And we employ the methods developed by Wang Hua Chen, which at the time in which this is work, it was the best methods that were out there. The experiments by Peter are done in bulk graphene with connected to metallic contacts. We cannot do that, but we can do graphene nanoribbons. And what we make sure is that these graphene nanoribbons, we take geometries that such that these graphene nanoribbons are metallic to mimic the behavior of the graphene in bulk. Okay. So this, and the main person that did all these calculations it's Antonio Garzón, who is now a postdoc at Northwestern. This was his PhD work. Okay, so let me show you maybe 3 or 4 years of simulation in the results of simulations in one slide. Okay, so what Antonio did is that he had this graphene nanoribbon connected to metallic electrodes. This is the electric field of light. So as you see, it just has a few cycles. The laser, the frequency that we use is the one that is using the experiments, which is typically around 800 nanometers, so 1.5 to 1.7 electron volts, something like this, of photon energy. And what I'm plotting here is the amount of charge that is extracted as a function of time. So it's not the current, but it's the integral over time of the current. So it's the net charge that is extracted out of this junction as a function of time. And this is for a Kerr envelope phase of pi halves, and this is for a Kerr envelope phase of 0. And what Antonio did is that he considered 3 types of junctions. One, so they're all 5.2 nanometers in width, but the length of it can be either 21 nanometers, 42 nanometers, or 85 nanometers. So a small, medium size, and a large junction, with the smaller one shown in black and the larger one in blue. Okay. So let me focus on the dynamics for a Kerr envelope phase of pi halves for the laser field first. So this is the amount of charge that is extracted as a function of time. And you see, during the laser field, you see charge moving back and forth in the junction. And just after the laser field is off, no net charge has been extracted out of this junction. But once that laser field is off, so once you completely turn off the laser field, what you see is that the amount of charge that it's extracted grows linearly in time, and then it oscillates. So what's happening is that your laser field is creating an electron hole wave packet. That electron hole wave packet moves, has a kick in momentum, and it moves toward the electrodes. And as it moves to the electrodes, you see the amount of charge that you extracted of this junction increases linearly. And once it reaches the interface between the graphene nanoribbon and the electrode, part of that electronic and hole wave packet will be absorbed, but part of it will bounce back. And because it bounces back, what you see is that the charge that is extracted sort of changes direction, no? And then you see these oscillations, and eventually it will settle to a constant value. Okay, so you see all the symmetry breaking here. This is the symmetry breaking, and all the symmetry breaking is happening after the pulse, no? The other thing to notice here is that as you go from the small junctions to the medium-sized junction to the longer junction, the magnitude of the effect increases, no? And the reason for this is because the photoactive area of the junction is increasing. And the other thing that is happening is that these oscillations of electrons in the junction become slower as you increase the system size, simply because it takes longer for the electron to move back and forth in this nano junction. So the two main things is that the magnitude of the effect increases with length. There is no net charge extracted during the laser pulse, and then you're really launching an electronic wave packet after the laser pulse that is responsible for this symmetry. Okay. Now, let me show you results now for a Kerr envelope phase of 0. And this is exactly the same type of calculation, exactly the same system. And the only thing that we're changing is that we're changing the Kerr envelope phase of the laser from pi halves to 0. And the results are shown here. And you see, the dynamics is completely different. What you're seeing is that all the contributions to the current happen during the laser field. So you see, it is during the laser field that I get a net contribution to the charge that is extracted, and after the laser field, nothing goes on. Okay, so whatever I'm doing, the net charge that I'm able to extract is only during photoillumination, and we assign this therefore to what we call virtual charge currents. And now, because this is an interfacial effect, it's independent of the size of the junctions, and you see that you get about the same effect for a 21 nanometer, 42, 185 nanometer junction. Okay, so it's independent of this. For reasons that I don't have the time to explain right now, actually this effect due to the Kerr envelope to the virtual charge carriers is robust to decoherence. Okay, so now if there is any truth to this, if there is any truth to the simulations, then as we go from a small junction to an increasingly large junctions, while the virtual charge carriers will remain approximately constant, the influence of the real charge carriers in the control become increasingly more important. So with a bit of luck, what we should see is that for small junctions, the virtual charge carrier should dominate, so the control should be at a Kerr envelope phase of 0. And as we increase the system size, the maximum of the controls should transition to a Kerr envelope phase of pi halves. So, and this is exactly the experiment that Peter, and in particular Christian Heide and Toby White did. So what they did is that they constructed a 5 micrometer junction connected to golds, a 2 micrometer junction connected to golds, a 1 micrometer junction connected to golds. The polarization of the laser field is across the junction direction. The laser spot size is about 1.5 micrometers in radius. So this, I mean, these laser spot size will be indicative of what they're doing. And again, what they like, the way that they like to plot the results is that they increase the laser amplitude radially from 0 to 1 to 2 to 3 volts per nanometer. If the current is positive, is red, and if the current is negative, is blue. And what they plot is the Kerr envelope phase of the laser radially. So this is a Kerr envelope phase of 0. This is a Kerr envelope phase of pi halves. And you see, when you are in the long junction, you get that the maximum of the current is at a Kerr envelope phase of pi halves. And according to our calculations, this means that the real charge carriers are dominating the control. But as you decrease the size of the junction, from 2 to 1 micrometer, what you're seeing is that the maximum of the control is no longer at pi halves, but is somewhere in the middle for the 2 micrometer junction. And while for the 1 micrometer junction is even closer to 0 or pi. And so what this is telling you is that you're transitioning the mechanism for the generation of currents from one in which the real charge carrier dominates to one in which the virtual charge carrier dominates for the small junctions. So we were very excited about this because we had discovered two contributions to the generation of currents. And not only that, but we discovered that we could disentangle them and that we could trigger them individually simply by varying the carrier envelope phase. So we sent this to a nice journal. And Toby, before sending it to the nice journal, what he added one paragraph in there that said something along the lines that because we had control over these two mechanisms for the currents, the real charge carriers and the virtual charge carriers, then that we could use this to develop logic gates that operate on femtosecond timescales. And the editor came back saying that this was a very nice contribution, but that if we could really demonstrate that last thing that we had in that last paper, it will be an even better paper. Okay, so then I had nothing to do with this. This is all Toby. He went back to the lab and closed the door, and he emerged with this picture a couple of months later. So what he did is that he had the 5 micrometer nano junction, and this is gold, and this is the graphene, and this is the gold. And he took a laser field and put it right at the center of the junction, such that it will induce only these real charge carriers. And he had another laser field, and he put it at the interface, such that it will induce only what we call now the virtual charge carriers. And what he could control was the phase of the laser at the center of the junction, laser A, and the phase of the laser at the interface between the graphene and the gold. So, and what he plots here is the current as a function of the difference in phase between the A and B lasers. And for technical reasons, he can only plot here the absolute value of the current. But let me just walk you through this. So he can choose the phase of the laser A to be pi halves or to be minus pi halves. If it's pi halves, it will lead, in these particular conditions, it leads to a current to the right, while if it's minus pi halves, it leads to a current to the left. And then for the laser B, he can choose that phase to be either pi halves or 0. If it's pi halves, it doesn't generate a current at all, because that's when the virtual charge carriers are eliminated. So this is what he means there. But if it's a current of 0, it will generate, if a phase of 0, it will generate a current to the left. And what Toby did is that he balanced the laser amplitudes such that the currents induced by laser A and B could cancel out completely. So for example, for this particular scenario in which the difference in currents are 0, so you will have a net current that will be positive, and this is in fact what is measured here. For this particular scenario in which the phase of A is pi halves and the phase of B is 0, the currents will cancel one another completely, and this is exactly what is shown here. For this particular scenario, the current will be to the left, and this is what is shown. This is the absolute value of the current, so it should be negative, but this is what is shown here. Okay, so now this was the idea. You can assign a logic value of 0 if the phase of laser A is pi halves, so this will be, or a logic value of 1 if the phase of laser A is minus pi halves. And similarly, you can assign a logic value of 0 if the phase of laser B is pi halves, and a logic value of 1 if the phase of laser B is 0. And then you can say that you get a 1 if your current is positive and more than certain value, and a 0 if it's negative or less than that threshold value. And what you see is that if you construct it in this way, what you have generated, it's a logic NOR gate, in the sense that this is your input from the laser field and this is your logical output, with the caveat that this is a logic NOR gate that operates on femtosecond timescales. So this is, I think, the example of the fastest example of information processing that have been produced so far. And the idea is that if you're able to do information processing on femtosecond timescales, you will eventually be able to do electronics and information processing at petahertz frequencies, which is about 1 million times faster than the state of the art. Okay. Okay, so just to summarize this, this is the paper, the light field control of real and virtual charge carriers. We can control electrons in matter on an ultra-fast timescales using few cycle lasers with stable carrier envelope phase. The optical generation of currents has contributions from both real and virtual charge carriers. These two contributions can be disentangled as they emerge from distinct carrier envelope phases for the driving laser. And these two mechanisms can be used to develop logic gates that operate on a femtosecond timescale, opening the way for petahertz electronics. And what this has meant for me personally, this is more like a personal experience in this whole direction. You see, this started for me as a dream of a PhD student. We had this early theoretical proposal in 2007 that eventually motivated very exciting experiments by the friends Krauss and Peter Holmhoff. And these experiments led us to develop better theory, and in particular, the integration of time-dependent non-equilibrium Green's functions and laser-induced dynamics. And now the combination of new theory and better experiments had led to the discovery of new physical phenomenon and perhaps to the development of new technologies. And this is a paper that we published with Peter. Okay. So if I have a couple of, maybe a few minutes left, I want to introduce this other scenario. Yeah, see, Carla, I have a few minutes. Okay, so I want to introduce the second scenario, which we call Shelly for the start control of electrons across interfaces, which is actually quite related to what I talked about, and I think it will give you a broader picture of how to control electron dynamics on ultra-fast timescales using the subcycle structure of light. Okay, so when you think about the problem of laser control, this is all based on quantum interference. And so the rule of thumb of quantum control is that if you lose coherence, you lose control. And the issue is that the electronic decoherence in matter is very fast, something like tens of femtoseconds. So what we do in Rochester is that we try to understand the decoherence very well, but we also design laser control strategies that are robust to the decoherence. And in particular, our route to this control has been through the Stark effect. So in the traditional Stark effect, what you will have is a material, maybe represented by this two-level system. You apply an electric field, and this will shift energy levels. And in the dynamic version of the Stark effect, or one dynamic version of the Stark effect, that electric field will be time-dependent, and now these energy shifts will be time-dependent too. And this is a form of Hamiltonian control. Is done but the way that you do it is through non-resonant lasers of intermediate intensity. That means that they are non-perturbative. You cannot capture them through finite order perturbation theory, but they're non-ionized. Okay, so the main advantage of this type of scenario is that it's a reversible laser matter interaction, and it's actually robust to decoherence because you're not using the fragile properties of superposition states, but you're really pushing electrons around. Okay, so let me show you this main concept behind Shelly. So here's the idea. You may have an interface, for example, a metal and a semiconductor or two semiconductors, and this may be your pristine interface. And what we're going to do is that we're going to apply very strong laser fields that distort the electronic structure. And what it will do, maybe in the Stark-driven material, the interface will look like this, or maybe like this for the semiconductor. And now what you're able to do is that you are able to generate resonances between occupied levels of one material and unoccupied levels of the other material. And now you can induce electron transfer across that interface that was previously forbidden. So let me show the basic example, and Carla, let me know when I should stop. Say, for example, you have two semiconducting materials, so semiconducting material A and semiconducting material B. This is the valence band, that's the conduction band, and this will be some form of metallic contact. And the way that I have concocted this problem is that it's a perfect insulator, and it's insulated to an applied voltage and also to resonant light-induced charge transfer, because if you photoexcite from the valence band to the conduction band, those photoexcited electrons will go back to the electrodes and then back to the valence band, and no net current will flow through this material. But now the idea is that you come in with a laser field that is very strong. You will distort the electronic structure. you will create transient resonances between the valence band of A and the conduction band of B. And now you will open new previously forbidden channels for electron tunneling across this interface. So let me show you how that works. So here it's a one-dimensional model. This is material A, this is material B. There's some interface, and you apply a static electric field. And what that electric field does is that it leads to fanning out of the energy levels. This is the Stark effect. And you see, you get many crossings between the levels of material A and the levels of material B. But most of those crossings, even when they cross in energy, they will be trivial crossings in the sense that, sure, they cross in energy, but these two levels will be not talking to one another at all. But every now and then, you get a crossing, for example, as this one that is highlighted here, in which this is the valence band of material A, and this is the one level of the conduction band of material B. And if you zoom in, what you find is that is not a trivial crossing, but there is an anti-crossing, no? And that means that now you have the possibility of inducing electron tunneling from this level of material A to this level of material B. And the reason why there is an anti-crossing is because the electric field is so strong that it localizes the energy levels of electrons in essentially just a few sites. And these two particular energy levels are located right at the interface. So now those electronic levels will be talking to one another. Okay, so that's Shelley. So just to convince you that this works, this is model quantum dynamic simulations in a model 1D tight banding chain. And what you're seeing is this is the amount of charge that is transferred from A to B. This is the type of energy level alignment. And what you're seeing is that this few cycle laser structure, it creates these opportunities for transfer from A to B via quantum tunneling. And these are due to the Stark effect. Now, the effect is robust. This is the Shelley effect as a function of laser amplitude. And you see, for very weak laser fields, you get nothing because there are no effective crossings. Then there is a region where you get effective crossings mainly between valence band of A and conduction band of B. And if you keep increasing your laser field, you get very complicated dynamics. I should probably be wrapping up, but the effect is robust to laser frequency. The lower the laser frequency, the better, because it leads to more effective quantum tunneling across the interface. The stronger the interfacial coupling between the two materials, the stronger the effect. It works with materials that have partial spectral overlap between their levels, which is the usual case. And we have also tested it in the context of screening and band bending. And while these effects do reduce the magnitude of the effect, they do not kill it, but it just partially reduces it. You can use it, for example, to generate currents in systems that are centrosymmetric, like ABA. This is the type of phenomenon that we will get. This is the amount of charge that you can extract out of this centrosymmetric material as a function of laser phases. And most recently, we have shown that this also works at the metal semiconductor interface. So it's not only semiconductor, but it could also work at the semiconductor molecule and the metal molecule interface. So it's a general phenomenon. So just to summarize, we developed a general scheme for the laser control of electrons at interfaces based on open quantum tunneling pathways through the Stark effect. This is what we call Shelley. This control is robust to laser parameters, energy level alignment. In fact, it's quite robust to decoherence, is robust to screening and interfacial effects, and it illustrates the power of Stark-based strategies to control electron dynamics. The charge transfer that you can generate is faster than what you can do through regular photoexcitation because it is controlled by the subcycle structure of light. You're really using the subcycle structure of light to generate this type of control. And with that, let me thank you for your attention. Thank my group for their really fantastic group of individuals that they do amazing things every day. And in particular, the work that I showed today is work done by Antonio. And we try to maintain worldwide collaborations, and these are some of our collaborators around the world. Thank you so much.
Well, thank you so much. It was a really great talk. Other questions, comments, please write in the Q&A tab or raise your hand if you would like to ask something. I mean, one question just to start that I do have is you mentioned when we were talking about those virtual charge carriers and interfacial effects, that they were robust to the coherence. And that seemed quite interesting because, at least for a naive person, it's not what you expect. Could you elaborate on that?
Yes, so it's sort of related to the reason why the Shelly effect is also robust to decoherence. So the reason why you get currents in that context is because you're pushing energy levels around such that they have the right alignment with the gold, such that you can extract charge. And this process of the energy level alignment, it has nothing to do with creating superposition states, but it has all to do with just pushing energy levels around, and then those effects are less sensitive to decoherence. They're affected a little bit, but they're quite robust. So that's a general phenomenon that happens when you're thinking about the start control of the control of electrons using ultrafast laser sources, in which you're using a Stark effects or energy level alignment, or just something in which you're pushing electrons in one direction. That tends to be quite robust to decoherence, while if you're using superposition states that need to live after the laser field, that tends to be quite fragile to the decoherence.
Okay. Are there questions? I mean, I know it's a Friday and people are a bit tired, but please raise your hand. It's always a good opportunity to talk to our speaker. And it is really fascinating that we have seen the shortest or the fastest logical gate ever so far. So for people who are interested in quantum technologies, this is really, really great to see. Chris, go ahead. You should be able to unmute yourself now.
Okay, do you hear me?
Yes.
Yeah. Ignacio, great talk. Thank you very much. I have a question for you, actually. I was thinking as you were talking about this, the first part of the talk, what this would look like if you were able to put a diode material in place of the graphene. I'm wondering, maybe this isn't a good question to ask because the way this works is through the symmetry breaking. But I'm just curious if you've thought about ways that you might be able to, make new kinds of logic gates if you had a diode in between the electrodes.
So we haven't explored that direction, but it's certainly a fascinating direction. You can, in most materials, so Chris, by the way, thank you for your talk and wonderful to see you. Thank you for being here. So in these materials, in most materials, what you will have is an effect that doesn't depend on laser phases, no? And the experiments work hard at getting rid of all these effects and just focus on the effects that depend on the carrier envelope phase. And they do this by a clever trick in where they're changing the carrier envelope phase, and they have a frequency for this, and they lock in with a lock-in amplifier. The reason why people don't focus on those effects is because while those effects exist, they're hard to control using laser phases. So if I change the carrier envelope phase from 0 to pi halves, or from pi halves to minus pi halves, that diode effect that you will get, it will always be there, and the control that you will be able to get is very small. No, so you will get a very strong effect, but it will not be laser phase controllable. And for this reason, is not something that we can exploit by using the techniques of quantum control.
Thank you.
Thank you. We have a question from an anonymous attendee. Under such a strong field, will ionization from graphene to the vacuum photoemission take place? And how important is that?
Yes. So in general, what you want to work is in a regime where you are not photoionizing, no? But photoionization can happen. And in fact, there are many other effects that can happen, because you have a laser field interacting with a metal electrode, and this interaction is very strong. And while all these effects happen, or may happen, the trick in the experiments is to only look at the part of the response that depends on laser phases. And all these complications, this is what changed this field. All these other complications, this is what Agustin Schrieffer and Ferenc Krauss did in their experiment. All these other complications that you can have, the response of the metal to the laser field, effects like photoionization, all these things, because they do not depend on the carrier envelope phase, they do not enter into the signal that they lock in during the measurement, and therefore they're able to explore this physics at play.
Is that clear? Would you like to pursue this question, or is that fine by you? It seems okay. They haven't replied. So are there further questions? It's a good opportunity, so raise your hand. And if you would like also to ask questions more privately, we're going to stop the live streaming soon. So there will be the opportunity to talk to our speaker. But it is really nice to see more and more how fascinating solids and strong fields is. We always learn quite a lot of things and quite a lot of applications as well. So for those who are watching on YouTube, we're going to stop the live streaming. Take good care of yourselves. Thank you for supporting us. Stay safe. And this is the last talk of the season, in fact. So we'll see you in October.